All right. Um, let's 1 sec. Let's just. All right. Okay. Um, I started learning about this stuff last night. I didn't take any notes, mostly because I was really struggling. So let's try and get it today. Let's see. Can I make this? There we go. I go home tomorrow, which will be good. Yeah. Um, for data that is used only internally within your organization, there's less pressure to use a lowest common denominator encoding format. Sure. For example, you could choose a format that is more compact or faster to parse. For a small data set, the gains are negligible, but once you get into the terabytes, the choice of data format can have a big impact. JSON is less verbose than XML, but both still use a lot of space compared to binary formats. This observation led to the development of a profusion of binary encodings. Of a profusion. Binary encodings for JSON, message pack. These formats have been adopted in various niches, but none of them are widely adopted, or as widely adopted as JSON or XML. Some of these formats extend the set of data types, but otherwise they keep the JSON. Um, Let's look at an example. Okay, so the first byte is A3 indicates that what follows. Okay, so we have an object. Ah, 8 is probably. I see. 8 is the data type. Just like 9 is the data type here, and then 2 is the number of entries. 1, 2, 3 is the number of properties, okay? The second byte indicates what follows is a string that is 8 bytes long. Zoning out, come on. Fuck, I'm zoning out so hard. Come on. Okay. So B is the length. A, just like here, 6, A6. A is the indicator that, okay, I think I understand that now. I was looking at this last night and I didn't quite understand what the top number meant. Okay. Apache Thrift, protocol buffers, protobuf, are binary encoding libraries that are based on the same principle. Protocol buffers was originally developed at Google. Thrift was originally developed at Facebook, and both were made open source. Both Thrift and protocol buffers require a schema for any data that is encoded. To encode the data in example 4.1 in Thrift, you would describe the schema in the Thrift interface definition language. The equivalent schema definition for protocol buffers looks like that. Yeah. And then Thrift and protocol buffers each come with a code generation tool that takes a schema definition like the one shown here and produces classes and implement the schema in various programming languages. Encoding example 4.1. So type is 11, field tag 1, length 6. So each field has this indicator, okay? And then what follows is a length, right? Not necessarily. I don't understand these ones here. Ah, it's because it's a list. So we have a string, field tag, so what property, so the property name, then length, okay, then value. So tag, so an int, property name, value, tag, property name. Now, because it's a list, we have type, length, item type string, oh, list type, and then we say how many items are in it, and then the length of the string, the length of the next string, and then end of struct. Similarly, I zoned out. The thrift compact. I'm like not even taking notes again. But these are like really specific. It packs the same information into only 34 bytes. It does this by packing the field type and tag number into a single byte and by using variable length integers. Rather than using a full 8 bytes for the 1337, is encoded into 2 bytes with the top bit of each byte used to indicate whether there are still more bytes to come. This means numbers between minus 64 and 63 are encoded only 1 byte. Numbers 2 bytes, the bigger numbers use more bytes. Okay, so where's that 1337? Ah. So this is if there's more, there is. Now there isn't, so it's over, and then this is reserved. Interesting. Okay. So probably should write something here. Since we can fit our requirements. Good enough. We said previously that schemas inevitably need to change over time. We call this schema evolution. How do thrift and protocol buffers handle schema changes while keeping backward and forward compatibility? As you can see from the examples, an encoded record is just the concatenation of its encoded fields. Each field is identified by its tag number, the numbers 1, 2, and 3, in the sample schemas, and annotated with a data type, example of string or integer. If a field value is not set, it is simply omitted from the encoded record. From this, you can see that field tags are critical to the meaning of the encoded data. You can change the name of a field in the schema, since the encoded data never refers to field names, but you cannot change a field's tag, since that would make all existing encoded data invalid. So let's go back real quick. We said previously that schemas inevitably need to change over time. We call this schema evolution. How do thrift and protocol buffers handle schema? So I use protocol buffers. I feel like this is important. handle schema changes while keeping backward and forward compatibility. As you can see from the examples, an encoded record is just the concatenation of its encoded fields, yeah? Each field is identified by its tag number, yeah? And annotated with a data type, yeah? That's like what I was trying to say in the sentence I just wrote. If a field value is not set, it is simply omitted from the encoded record. From this, you can see that field tags are critical to the meaning of the encoded data. Yeah, you need context, right? If you don't have the protos, like if you don't know what the tags are, then you can't determine what's going on. You can change the name of the field in the schema, since the encoded data never refers to field names. Okay, but you cannot change a field's tag, since that would make all existing encode. Yeah, so if you went from like 5 to 6, that doesn't work, but you can, the field name is arbitrary. You can add new fields to the schema, provided that you give each field a new tag number. That's why I've tried to write protobuf before, and when I was copying and pasting, I accidentally forgot to change the number. I never knew why it was going up, but now I do. That's cool. I need to blow my nose real quick, but this is very productive. Okay. You can add new fields to the schema, provided that you give each field a new tag number. If old code, which doesn't know about the new tag numbers you added, tries to read data written by new code, yeah, including a new field tag with a tag number it doesn't recognize, it can simply ignore that field. So you can send data that has extra tag numbers, and it just doesn't matter because the decoder won't recognize it and just simply skip it. Okay. The data type annotations allow the parser to determine how many bytes it needs to skip. Yeah. This maintains forward compatibility. Old code can read records that were written by new code. Cool. What about backward compatibility? As long as each field has a unique tag number, new code can always read old data because the tag numbers still have the same meaning. You cannot make it required. Okay, so if you update a proto, it cannot be required. Huh. Okay. What's RPC? What's it called again? Of the so Data types and schema evolution. What about changing the data type of a field? That may be possible. Check out the documentation for details, but there is a risk that values will lose precision or get truncated. For example, say you change a 32-bit integer into a 64-bit integer. New code can easily read data written by old code. Because the parser can fill in any missing bits with zeros. However, if old code reads data written by new code, the old code is still using a 32-bit variable to hold the value. If the decoded 64-bit value won't fit in 32 bits, it will be truncated. So this is expected, right? That totally makes sense. A curious detail of protocol buffers is that it does not have a list of array data types, list or array data type, but instead has a repeated marker for fields, which is a third option alongside required and optional. As you can see, oh, I see. So repeated. I don't understand this. Hold on. Where's the repeated? I don't see this. Figure 4, 4. Oh, it's saying that the field tag might be repeated. Okay, okay. Okay, and because of that, it would like decode the first one, see field tag 3 again, and then decode the second one. I see. So new code reading old data sees a list with 0 or 1 elements. New code, yeah. Depending on whether the old code reading new data sees only the last element of the list. Okay. Additionally, need to do this. Oof, that's brutal. Okay, so we'll stop here. We'll get some cards done, and then we'll try and do cards till the end. So let's just adjust real quick to get a few minutes in here. Close this. Open this one. Oh, I think actually if I just... Yeah, okay. And then flashcards. So scalability is a system's ability to handle to perform more operations, whatever they are, for a set amount of time. The term we use to describe the system's ability to cope with increased load. Throughput is the amount of work over a given amount of time. The number of records we can process, or the total time it takes to run a job on a data set of a certain size. A failure is when the system stops operating, is unable to respond. Stop servicing users, okay. What are the key characteristics of the relational model? SQL, tables and schemas, joins, indexes, decades of tooling, that's the last one. SQL, normalization and strong consistency. We'll say this is hard. Normalization is when we remove duplication from the database, from the data set, I should say. The practice of reducing duplication in the system, okay, by having predefined human relevant info. Duplication in data models refers to when human relevant information is stored multiple times. This leads to each record storing its own piece of information rather than referencing one. What is the graph data model best suited for? What is the graph data model best suited for? Data model best suited for social networks, network topology, recommendation engines. What are the downsides of imperative queries embedded in application code? There's so many. Downsides of imperative queries embedded in application code. Tight coupling with business logic. Not harder to debug. Performance. Harder to optimize, yeah. Error prone. We'll say this is good, and then we'll stop here. We'll do more tomorrow. All right.